Have you ever noticed how quickly a hot cup of coffee cools down? Or maybe how your freezer stays really frosty inside even when it's boiling hot outside?
Mm.
We experience heat transfer all the time, but have you ever stopped to think about how heat actually moves through things?
Yeah, it's more complex than just hot to cold.
Exactly. It's got this precise, almost mathematical logic behind it.
It really does.
Welcome to the deep dive. This is where we take your sources, could be articles, research papers, even your own notes, and we dig into them to pull out the most important bits of knowledge.
Get right to the core ideas.
Today we're diving deep into thermal physics, specifically the heat conduction equation, our mission, to help you understand how temperature changes and heat flows through different materials.
And hopefully reveal some, surprising connections to everyday stuff and engineering.
Okay, so let's start with something really crucial, heat transfer. It isn't just a simple value, is it?
Not at all. It's got both direction and magnitude. It's fundamentally different from temperature in that way.
Right, like temperature is just, say, 18 degrees Celsius on your wall, a single number at a single point.
Mm. But heat transfer, or heat flux,
Hmm.
if someone says 50 watts per square meter, the immediate question has to be,
Which way? Is it coming in, going out?
exactly, you absolutely need that direction.
And what's driving all this movement?
Well, that's the fundamental thing. It's always a temperature difference. Always.
Like a hill for energy.
Precisely. Think of it like that. The bigger the temperature difference, the steeper the hill, the greater the rate of heat transfer. It's the push.
Okay, let's unpack this a bit more. Because time plays a big role, and so does the actual space heat moves through. It's not static.
No, definitely not. We often classify problems based on time dependence first. Is it steady or transient?
Steady meaning unchanged.
Right. Imagine your house heating system has been running for hours.
Mhm.
Inside temp is constant, outside temp is constant. The heat flow through the walls settles into a steady state. Temperature at any given point isn't changing over time.
Okay. And transient.
That's when things are changing. Like you put an apple in the fridge, its temperature drops minute by minute. That's transient or unsteady heat transfer.
So things are constantly shifting.
And what's interesting is that most real-world problems are actually transient, but engineers, they often analyze them assuming steady conditions.
Why do that? Isn't that wrong?
Well, it's a simplification, but a very useful one. Steady problems are much easier to solve mathematically. And often, for design like figuring out the biggest heat loss to the size of furnace, the steady-state answer for the worst case is good enough. It gives you what you need.
A practical shortcut.
Exactly. Oh, and there's also a special transient case called lumped systems. That's when an object is small or conductive enough that its temperature changes pretty uniformly throughout. Think of a tiny metal bead cooling down.
Okay, I see. So we've got time dependence. What about space?
Right, the spatial dimensions. We also classify problems by how many directions the temperature changes in significantly.
One-dimensional, two-dimensional.
Yeah. One-dimensional, or 1D, means temperature really only varies along one main direction. Heat flow in the other directions is tiny, negligible, basically.
Like heat going straight through a window pane, perpendicular to the glass.
Perfect example. Or heat moving radially out from a long hot water pipe. Or even heat going into a boiling egg if you assume it's perfectly spherical. The symmetry makes it 1D radially.
Makes sense. And 2D.
Temperature varies mainly in two directions. Imagine a long metal bar with, say, a rectangular shape. If it's long enough, the temperature changes across the rectangle, but not much along its length. That's 2D.
And 3D is everything varying.
Pretty much.
Mm-hmm.
Temperature changes significantly in all three directions. That's the most general and usually the most complex case.
So understanding this means choosing the right way to visualize the heat flow is half the battle.
It really is. And choosing the right coordinate system is part of that.
Ah, like rectangular, cylindrical.
Exactly. You pick the system that matches the geometry. Rectangular for boxes, cylindrical for pipes or rods, spherical for, well, spheres. It just makes the math line up properly.
Okay, so we've got the context, time, space, direction. What's the actual rule, the physics governing this movement?
Now we get to the heart of it. It's Fourier's law of heat conduction.
Fourier's law, okay.
It's fundamental.
Yeah.
It basically says the rate of heat conduction, how fast heat moves in a certain direction, is proportional to two things.
The tar.
The material's thermal conductivity, how easily it lets heat pass through, and the temperature gradient in that direction.
Temperature gradient,
Yeah.
meaning how fast the temperature changes with distance.
Exactly, like the steepness of that temperature hill we talked about. Steeper gradient, faster heat flow.
And I often see a minus sign in that equation. What's that about?
Yes, the negative sign. It's crucial. It seems simple, but it just reflects reality. Heat always flows from higher temperature to lower temperature,
Yeah.
downhill. The math needs that negative sign to make sure that if heat is flowing in what we call the positive x direction, it means the temperature must be decreasing in that direction. It makes the heat flow value positive when it moves downhill along our chosen axis.
Got it. It keeps the direction straight. And you mentioned thermal conductivity, K.
It's K. That's a material property, super important. It tells you how good a material is at conducting heat. Metals like copper have high K. Insulators like foam have very low K.
Does it stay the same for a material?
Well, in reality, K usually changes with temperature, sometimes quite a bit. But for many engineering problems, especially over smaller temperature ranges, using a constant average value of K works pretty well and simplifies things a lot.
Okay. And you mentioned isotropic materials earlier.
Right, yeah. Most common materials are isotropic. Their properties, including K, are the same no matter which direction you measure. But some materials, like wood, are anisotropic. Heat travels much easier along the grain than across it.
Interesting. Different K values depending on direction.
Exactly.
Yeah.
But for today, let's stick with isotropic materials to keep things, manageable.
Okay. Now, what about heat that doesn't just pass through something? What if it's actually being made inside?
Ah, yes. Internal heat generation. That's a whole other layer.
So heat isn't just flowing, it's being produced.
Precisely. It happens when some other form of energy gets converted into thermal energy within the material itself. Think electrical energy, chemical, nuclear.
Heats of coils in my toaster. Or an electric heater.
Perfect examples. That's resistance heating. Electrical energy turns into heat right inside the wire. You gave the hairdryer example earlier. A 1200-watt dryer wire. It can generate something like 212 watts per cubic centimeter.
Wow, that's a lot in a tiny space.
It's immense. That's why cooling electronics is such a huge field now.
Yeah.
Chips generate so much heat internally, you have to get it out efficiently or they'll fry.
What are some other examples?
Well, nuclear reactors are a big one. Fuel rods generate enormous heat from nuclear reactions, like 70 million watts per cubic meter. Yeah. Then there's natural radioactive decay in some materials. Chemical reactions that release heat, exothermic reactions, or even radiation being absorbed, like sunlight warming up a lake, where the energy gets deposited throughout the water depths.
So the key thing here is that it happens inside the volume.
Exactly. Heat generation is a volumetric phenomenon. It occurs throughout the body of the medium, and we usually measure its rate per unit volume, like watts per cubic meter.
Okay, so we have heat flowing according to Fourier's law, possibly with internal generation. How do we put this all together mathematically?
That leads us to the big one, the heat conduction equation.
The grand unified theory you mentioned.
Well, for conduction, pretty much. It's the central equation derived by doing an energy balance on a tiny little chunk, a differential volume, inside the material. It accounts for heat flowing in and out and any heat generated within.
And it looks different depending on the situation.
Yes, it simplifies nicely depending on the geometry, flat wall, cylinder, sphere, and the conditions, like steady state or no heat generation. There's even a clever combined form that uses one parameter, n, to represent all three simple geometries. N for a wall, 1 for a cylinder, 2 for a sphere.
Neat.
It really is. And fundamentally, these equations, in their various forms, are what let engineers predict temperature anywhere inside an object and figure out how much heat is flowing. It's the blueprint for thermal design.
But just having the equation isn't enough, right? You said it's like a map with no starting point.
Exactly. You need more information. To get a unique, specific solution for your particular problem, you need to specify conditions at the boundaries.
Boundary conditions, or BCs.
Right. These are mathematical statements about what's happening thermally at the surfaces of your object. And if the problem is transient, changing with time.
You need an initial condition.
Yep, an initial condition, or IC. That tells you the temperature distribution everywhere inside the object right at the beginning, usually time t0.
How many of these conditions do you need?
Good question. It relates to the math. The heat equation involves second derivatives in space, like ddx-xt2 search. So you need 2 boundary conditions for each spatial dimension you're considering. One for time, though. It's first order in time, dddt, so only one initial condition is needed for transient problems, no matter how many spatial dimensions.
Okay, 2 BCs per direction, 1 IC for time. What kinds of BCs are there?
Several common types. The simplest is specified temperature. You just know the temperature on a surface, like maybe you measured it, and the inner surface of a pan is 110 degrees C. Done. That's your condition.
Easy enough.
Then there's specified heat flux. Here, you know how much heat is flowing across the surface, the rate, like watts per square meter? You have to be careful with the sign convention here. Positive flux usually means heat flowing out in the positive coordinate direction.
What if no heat flows across, like insulation?
That's a very important special case. An insulated surface. The heat flux is zero. Mathematically, this means the temperature gradient, the slope of temperature perpendicular to that surface, must be zero. The temperature profile is flat, right at the boundary.
And symmetry planes act like that too.
Exactly. If you have a plane of symmetry in your problem, no heat flows across it. So it acts just like an insulated surface. Zero gradient.
What's next?
Probably the most common one in practice, the convection boundary condition. Most surfaces are exposed to air or some fluid.
Right, like my coffee cup cooling in the air.
Perfect. This condition says the heat conducted to the surface from inside the object must equal the heat convected away from the surface into the surrounding fluid. It balances conduction and convection right at the interface.
Okay. What about radiation?
The radiation boundary condition. Heat exchange via electromagnetic waves, crucial for things in space, or very high temperatures, or cryogenic applications.
Anything tricky about that one?
Oh yeah, it's nonlinear. Remember, Fourier's law and convection are generally linear with temperature difference. Radiation depends on temperature raised to the fourth power, P.
T to the 4.
Yeah,
Wow.
TO. That makes the math much harder. Solutions often require numerical methods. It's why engineers sometimes try to simplify or linearize it if radiation isn't the dominant mode. And always remember, temperatures and radiation calculations must be absolute Kelvin or Rankine.
Good tip. Any other types?
Well, interface conditions are important when you have layers of different materials stuck together, like insulation on a pipe.
What happens at the join?
Two things must be true right at the interface. One, the temperature must be the same on both sides, no sudden jump. And two, the heat flux must be the same. Heat flowing out of material, A, must equal heat flowing into material, B. Energy is conserved.
Makes sense. Heat doesn't just vanish.
And finally, you often have generalized boundary conditions, where multiple things happen at once on a surface. Maybe convection and radiation happening together, or maybe there's a specified heat flux coming in, like solar radiation plus convection loss. You just add up all the effects.
Okay, wow. So equations, boundary conditions. How do engineers actually use all this to figure things out?
Right, the practical application. It usually follows a three-step process. Step 1, formulate the problem, write down the right form of the heat equation, and gather all your boundary and initial conditions. Get the setup right.
Step 1, setup.
Step 2, obtain the general solution of the differential equation. This will usually have some unknown constants in it.
Step 2, general math solution.
Step 3, apply your specific boundary and initial conditions to that general solution. This lets you figure out the values of those unknown constants, giving you the unique solution for your specific problem.
Step 3, make it specific. Okay, and we see how this works with an example, like that simple wall.
Sure. For a basic plain wall, steady state, constant K, no heat generation. We said the temperature profile is linear, a straight line.
Right.
Now, imagine you messed up the boundary conditions. Suppose you specified the heat flux coming in one side and the heat flux going out the other side, but you made them unequal, and there's no heat generation inside.
So more heat coming in than going out, or vice versa.
Exactly. If you try to solve that mathematically for a steady state, you find there's no solution.
No solution. What does that mean?
It means a steady state is physically impossible under those conditions. If more heat enters than leaves, the wall's temperature have to keep rising indefinitely. It can't be steady. The math perfectly reflects the physics. It tells you your boundary condition setup doesn't make physical sense for a steady state.
That's actually really cool. The math knows physics.
It does. Getting the BCs right is critical not just for getting a solution, but for getting the physically correct one.
Can we use this to find temperatures we can't easily measure?
Absolutely. Think about a clothes iron, maybe 1200 watts. The base plate is, say, half a centimeter thick. Heat comes in uniformly from the element inside and convects out the bottom to the clothes.
Okay.
Let's say you measure the outer surface, the part touching the fabric, and it's 85 degrees C. Using the heat equation and the convection condition, you can calculate the temperature of the inner surface right next to the heating element. It might turn out to be, say, 100 degrees C.
So you can find the temperature inside without drilling a hole.
Precisely. It allows you to understand the temperature distribution throughout.
And this must have safety implications, too.
Huge ones. Consider an engine housing in a chemical plant. Maybe it's 1 centimeter thick steel. Heat is generated inside, let's say 6 kilowatts per square meter flows out through the inner surface. The outer surface cools by convection to the surrounding air at 35 degrees C.
Standard setup.
Now, suppose there's oil used nearby that auto-ignites, catches fire on its own if it touches a surface hotter than 250 degrees C.
Okay, potential hazard.
You run the heat transfer calculation for the housing under normal operation, and you find the outer surface temperature reaches 335 degrees C.
Uh-oh. That's way above the ignition point.
Exactly. The analysis immediately flags a major fire hazard. Before anything bad happens, the calculation tells you need to add insulation or improve cooling to get that surface temperature well below 250 degrees C, maybe aiming for under 200 degrees C, just to be safe.
That's powerful. Prevention through calculation.
It's a core part of engineering design and safety analysis.
What about other shapes, like pipes or spheres?
Same principles apply, just using cylindrical or spherical coordinates. For instance, a long steam pipe, maybe 20 meters long, inner radius 6 centimeters, outer 8 centimeters. If the inner surface is 150 degrees C and the outer is 60 degrees C.
You can calculate the total heat loss.
Yep. You use the heat equation in cylindrical coordinates, apply the temperature boundary conditions, and integrate. You might find it's losing, say, 786 kilowatts of heat. That's a lot of energy escaping. Tells you maybe you need better insulation.
And for spheres?
Similar idea. You can calculate heat loss from spherical tanks. But here's an interesting point for both cylinders and spheres. While the total rate of heat transfer, watts, stays constant as you move outward through the wall, assuming no generation, the heat flux, watts per square meter, actually decreases.
Decreases? Why?
Because the surface area gets bigger as the radius increases.
Yeah.
The same amount of total heat is spread over a larger area, so the flux, the intensity, goes down.
Ah, okay. Area effect. Makes sense.
Yeah. For a sphere, the area goes up as radius squared, so the flux drops off even faster than for a cylinder where area increases linearly with radius.
Okay, let's go back to that internal heat generation. If heat is being made inside something, like a battery charging or that nuclear fuel rod, where does it get hottest? Is it near the surface where it's trying to escape?
That's a great question, and the answer is often counterintuitive. For simple symmetrical shapes, a flat wall, a long cylinder, a sphere with uniform heat generation inside, and a constant surface temperature outside,
Yeah.
the maximum temperature is always at the center.
Always at the center, not the surface.
Always at the center. Think about it. Heat generated right at the center has the longest path to travel to get out to the surface. Heat generated near the surface has an easier escape. So the temperature builds up most right in the middle, the midplane of the wall, the center line of the cylinder, the midpoint of the sphere.
Okay, that makes sense when you put it like that. The longest journey out.
Exactly. And engineers have specific formulas derived from the heat equation to calculate exactly how much hotter the center is compared to the surface for these cases.
Can you give an example?
Sure. Remember that 2 kilowatt resistance heater wire, 4 millimeter diameter. Let's say its outer surface is measured at 105 degrees C.
Okay.
Using the formula for a cylinder with internal heat generation, you could calculate its centerline temperature to be maybe 126 degrees C.
So a 21-degree difference just from the surface to the very middle.
Yep. And that 21 degrees could be critical. Maybe the core material starts to degrade above 120 degrees C.
Yeah.
Knowing the peak temperature is vital for design.
Definitely. What about more complex things, like layers?
Yeah, composite materials are common. Imagine that resistance wire, but now it's embedded inside a layer of ceramic insulation.
Yeah.
You'd solve the heat equation for the wire with heat generation, and for the ceramic layer, probably no generation, and you'd use those interface conditions, equal temperature and equal heat flux, where they meet.
So you track the temperature profile across both materials.
Exactly. You might find the wire center is, say, 153 degrees C. The wire ceramic boundary is 149 degrees C. And the outer surface of the ceramic is maybe only 45 degrees C. You get the full picture. Crucial for designing things like heating elements or electronics packaging.
This is making me realize how much detail goes into thermal design.
Yeah.
Now, you mentioned earlier that thermal conductivity, K, isn't always constant.
Ah, yes, the real world's curveball. Variable thermal conductivity.
How much does it usually change?
It depends on the material and the temperature range. For some materials over wide ranges, K can change significantly. It generally increases with temperature for gases, but can increase or decrease for liquids and solids.
And what does that do to our nice, simple solutions, like the straight line temperature in a wall?
It makes it not a straight line anymore. If K changes with temperature, The temperature profile through a simple wall becomes a curve.
A curve. Okay, so the heat flow isn't quite as straightforward.
Right. The conductivity changes as you move through the material because the temperature is changing. It adds a layer of complexity.
So how do engineers handle that? Do they always need complex solutions?
Often, they can still use a clever simplification. They calculate or look up an average thermal conductivity value, CAVG, over the temperature range the material experiences.
An average K.
Yeah. And what's really neat is that if the thermal conductivity varies linearly with temperature, which is often a decent approximation, then the correct average K to use in the simple constant property formulas is just the value of K calculated at the average temperature.
Oh, that's handy.
Yeah.
So find the average temperature across the wall, find K at that temperature, and use that K in the simpler equation.
Pretty much, for linear variation, yeah. For example, let's take a bronze plate, maybe zero point 0.1 meters thick. One side is hot, 600 Kelvin. The other cooler, 400 Kelvin. The average temperature is 500 K. If you know how K for bronze changes with temperature, you find its value at 500 K and use that single value, maybe it's 55.5 W in K, to calculate the overall heat transfer. It makes variable properties much more manageable for many practical cases.
That's a relief. Still allows for practical calculations.
It does. It's about finding the right balance between accuracy and simplicity.
Well, this has been quite the journey. We've gone from just thinking about hot coffee to Fourier's law, steady versus transient, boundary conditions, internal generation, even variable properties.
We've covered a lot of ground on the heat conduction equation, from the basics of direction and temperature difference,
Through the different types of problems and how to classify them in time and space,
to the crucial role of Fourier's law and thermal conductivity,
and that whole idea of heat being generated inside things.
plus the absolute necessity of boundary and initial conditions to get real answers.
And seeing how it all comes together to solve actual engineering problems, preventing fires, calculating heat loss. It's pretty amazing.
It really forms the bedrock of so much thermal analysis.
So here's a final thought for you, our listeners. Next time you feel something hot or cold, maybe your laptop getting warm, or you see steam rising from a pipe, think about that silent, precise dance of energy happening inside, governed by these equations we've talked about. Think about how understanding these rules lets us build safer cars, more efficient homes, better electronics.
It really connects the physics to the function.
What other hidden thermal stories do you think are playing out all around you in everyday objects, just waiting to be understood through the lens of heat conduction?